Morning, everybody. Thanks for coming. My name is Tran. These are my teammates, Flagler and Ingles. We're Team 6, and we're presenting the body cooling system. Our project is sponsored by Ronald Leader, who's here with us today. The purpose of our project is to design a lightweight, wearable garment that can cool the human body to comfortable levels. We want this to be hopefully in the future marketed, so we don't focus on cost efficient and also flexibility, and also properly insulated so we won't lose any cooling between our device and the human body. Some parameters we have to consider based off our situation we're doing. We chose to be the most applicable application of this will be in Miami in summer seasons, where our temperatures are usually around 92 degrees Fahrenheit, wind levels between like 70 to 80%. We chose our initial water temperature to start at room temperature around 78 degrees Fahrenheit for our testings. And also for our calculations, we know that we have different human body sizes, but we decided to use an average adult male for the torso alone, which is roughly around 0.342 meters square. The human body itself. The human body has pretty much an internal temperature of 37 degrees Celsius or 98.6 degrees Fahrenheit. The heat, as you see in the thermal images here, the heat is concentrated in the upper torso regions where the major organs are working, like the lungs and the heart. And the torso itself consists of 18% of the surface area and mass. For an average adult male, the total surface area of the whole body is about 1.9 meters square.
Okay, so for our theoretical analysis, the first step we did was to focus on from the core of the body of the human to the water in our copper tubing, and we decided to use a thermal resistance method to achieve this. As you can see in the table on the top, the Q that we were using in watts, our heat loss rate. We found that by looking at a study done by Cornell, there's a way to quantify the metabolic rate of individuals based on the activity they're doing. So we assumed the initial parameters were someone standing, and then the next parameter was light activities, walking, things like that. By calculating the respective wattage we emit in those activities, we took that difference, and that was the heat loss rate we wanted to maintain. To find the resistance of the components in between the core to the copper tubing is right here on display on the table bottom. To find those individual resistance, you have to take the thickness of the material divided by its thermal conductivity and times it by the area in which the heat is passing through. Using this method, we found that the temperature of the water that we have to be at to get away 44.23 watts is about 21.5 degrees Celsius. So the next study we did was, because we were using a Peltier plate as the main source of cooling, we had to find the effective QC and QH, how much heat is able to remove, and the resulting heat that's on the other side of the hot side of the Peltier. So those are the governing equations you see on the left. It was a very time-consuming process. But the main thing to get out of this is that for our specific Peltier and things like that, we found that the QC is about 15.14 watts, and on the respective side, the wattage on the hot side is about 95.17. And we also calculated some basic, how much voltage we would have to input into the system as well as the power to achieve that. And we found that the coefficient of performance for our specific Peltier was about 15.91%. And then, so for the next study we did was a simple thermodynamic study to find out how much heat we would need to remove from the water that's in our water block to achieve that. So we found the energy we would need to remove by taking the mass, which we assumed was 175 milliliters, convert that to grams, times it by the specific heat of water, and then times it by our temperature difference. Once we get that energy removed, we divide it by how long the devices will be operating for, which in our case is 15 minutes, convert that to seconds, and we found that the amount of heat we would need to remove from that water is equivalent to about 1.7 watts. And then the next step that was important is because when we extract heat from the water using the Peltier, the hot side, when we extract it from the cold side, the other side gets hot. So we need to find a proper way of dissipating that heat. So we're using a heat sink in which now we have to calculate the Q of that heat sink. That is done by the similar approach that we did with the human body, is a thermal resistance method, with, as you can see, the equation on the left. So once we calculate using those parameters, we found that the Q of the heatsink is about 75.5 watts. And then when we did another method or another testing to find how much heat can be dissipated through forced convection induced by the fan, as you can see in the top, we found that we were able to remove about 13.5 watts. So to find our delta Q net, basically how much heat is on the hot side of the Peltier, subtracted by the amount of heat that we found here on the heatsink, and then add that to the Q that we got from forced convection, we found out the delta Q net for our system, basically that how much we're able to dissipate and extract is about 33.1 watts. And then the last thing we did, because we have water going through this copper tubing, we did a flow analysis at the inlet and outlet of our copper tubing. So we used a modified version of Bernoulli's equation, in which, based on our frame of reference of where we chose the 2 points to be, there is no change in height difference, so the potential energy term in that equation can be negated, as well as comparing the mass flow rate from point 1 to point 2. We're not changing the fluid, nor is there any change in diameter. So as a result, the velocity at point 1 has to equal the velocity at point 2, so we can negate that term as well from Bernoulli's equation to get the modified form that you see on the left. Putting the parameters that we have with our specific, tubing and things like that, we basically found that the change in pressure in our system is equivalent to 58.9 psi. And when we researched based on the supplier's information of how much pressure our copper tubing can withstand, it was found to be about 1100 psi can withstand. So we are well below that tolerance.
We perform a flow simulation of our water block itself. You see the left side is the inlet and the right side is the outlet. And the pump right now is running at 12 volts. And we've seen the inlet pressure is atmospheric pressure of the environment, which is 1 atm or 14.7 psi. And we assume for outlet velocity is based off our pump's flow, which is around 4.3 meters per second, based off the pressure it creates from suction. And pretty much what we see here is that water is coming from the inlet, colliding with the back wall, and then being sucked into the pump, which is coming to the outlet. Which also verifies when I do our experimental results. When we saw the water block stuff, it was behaving exactly the same way our simulation displayed. Next we did was the thermostats of the water within the water block, so how cold you can get based off our settings. Again, we based off our initial settings of Miami summertime, and we put this running at constant capacity around 0 degrees Celsius for the cold side, while our setting temperature of the water is around room temperature of 78. And for this time lapse, we're doing a 10-minute study for now, and the target temperature we're trying to get again was 70.4 degrees Fahrenheit. The average temperature of the water within the water block was 68.7 degrees Fahrenheit, showing that within less than 10 minutes, the water was cool enough to start cooling the body. Next, we have a 15-minute study with our target time limit of 15 minutes. And again, our average temperature is around 66.4 degrees Fahrenheit when we measure the water's temperature. On a side note, that the time it takes to actually get to 70.4 degrees Fahrenheit was actually 8 minutes. Again, we also assume that it's during Miami summertime. Right now, when we do our experimental testing, we're now in winter, so it's not very hot outside as much as compared to the summer.
Okay, so quickly going over our cooling device. Our primary component, which is going to be used to cool the water inside of the water block, will be the Peltier device, as Victor and Michael has mentioned before. So the Peltier device is a device, an electronic device that takes a voltage input and can create a temperature difference. So to remove the heat from the Peltier, we have the heat sink fan. We also have, for the circulation of water, we have our water block pump. And to circulate, what that will circulate through will be vinyl tubing and copper tubing. And the entire system will run on rechargeable batteries. So here is a schematic of our cooling device. So the Peltier device will actually be oriented in between the heat sink and water block. So to get rid of any excess heat from that Peltier, we've used the heat sink, which will absorb a certain amount of heat from that hot side of the Peltier in order to dissipate any residual heat that the heatsink brings in, we also have a fan that will via forced convection, force that excess heat into the surrounding air. Now, for the cooling effect, we have a water block that's going to be filled with water. And what we did is before we actually send that water through our system, we wait about 10 to 15 minutes and get it down to our target temperature before sending it out. And that will effectively chill the entire system. And we also use a submersible pump just in case we have any water get onto our pump. It won't damage or break the pump. So our final design here, we have on the left side, we can see that we used a neoprene vest that's a stretchier material. And we also, to insulate it, we used a thick 1-inch neoprene foam, because neoprene foam we found to have a very low thermal conductivity. So that will protect the copper tubing that we're using that's going to be mounted onto the person's back. It will protect the copper tubing from absorbing any heat from the outside temperatures. And then on the right side, we have our cooling device that is mounted to the vest, and we decided to mount it using another sheet of neoprene foam. That way, there's no swaying of the device on the person's back, and it's stabilized. So from there, we have the vinyl tubing is attached to the water block, runs to the pump, and then afterwards it is sent to the copper tubing by the neck area, and the whole system will circulate back and forth throughout the system. So for some experimental results, like I said, our initial time, we did 15-minute intervals. So our initial temperature of the water and the copper is 81.7 and 80.4 degrees Fahrenheit respectively. So our final average temperature of the copper ended up being 70.2 degrees Fahrenheit, and our final average temperature of the water is 63.1 degrees Fahrenheit, which was still below our target, just below our target value for what we need the water to be in order to remove enough heat from the human. Now our simulations read 66.4 degrees Fahrenheit. So between our experimental data and our actual data, we got our experimental and our theoretical data, we got an error of 4.97%. And here is a cost analysis of the entire system. So for the total cost, we wanted it as low as possible. Our total cost ended up being $315.41 to produce. However, looking at the most expensive components, we have the neoprene vest, the neoprene sheet, and the batteries that it takes to power the system. So the neoprene vest, we decided to go ahead and go with one that was already pre-made. So that one was $61.94. So that, assuming we could use one that is a lot cheaper, we could definitely drive the price point down. The neoprene sheet, we actually didn't use the entire sheet that we had. So cutting that amount to what we actually needed would greatly reduce the price, because that's actually the most expensive component on this entire list. And then to the batteries are $5 each at multiply that by 14, we have $70 total for our batteries. So our batteries, if we could find another method of getting the right type of batteries to power it at a cheaper cost, then we could effectively decrease that price by quite a significant amount.
Alright, so these are the standardized organizations that we use for our project to make sure that our prototype follows regulations and standards. Global design is a big thing we're trying to implement in our university and our design itself. So one thing we need to include is we plan to market this to the general public as an instruction manual in multiple languages so that most people can understand how to operate the device. The materials we use, for the most part, are readily available around the world, so we wouldn't necessarily obstruct one nation over another if they decided to manufacture this. In the future, customizable options, because when you purchase something, sometimes you want to give it a sense of individuality, so there'll be customizable options for the thing. So flexibility is a huge thing that we need to take into account, because when someone's wearing this, they don't want their range of motion to be obstructed, so we have to make sure it's flexible. And because we want to sell this to people, we have to make sure that maintenance is easy so that it's not needed to go to a specialty shop. This is just a timeline from our senior ones all the way now to make sure that we follow in our pace with what we need to be. And some future improvements that we found after we completed the experiment was that we need a better combination of cooling to maximize, how much cooling we do to the person. Maybe, changing the dimensions of some of the materials we're using, for example. Adjustable garments, because we are all people of varying sizes and shapes. You don't want to make like a vest that only fit a certain person. You don't want to exclude people, so make adjustable sizes to accommodate all of those. We would like to integrate more tubing, as you saw, like James mentioned earlier, and you saw in the pictures. Right now we're focusing on the back portion of the individual, so if we can increase the amount of surface area of contact of that cooling, it would basically make the device better. Right now the water block we're using is made of acrylic, but we shaved off the bottom face and fitted it with aluminum, which that aluminum plate is going to be in contact with the felt gauge and increase how much cooling is applied. But in the future, we would plan to make the water block purely of aluminum to further increase that efficiency of cooling of the water. And like James mentioned earlier, we want to find more cheaper alternatives for the battery to power the device, so minimize power consumption to maximize our battery life. That's our presentation. Any questions?
Did you guys actually calculate your battery life?
When we did the experimental testing, at around the 45-minute mark, we saw a huge dissipation of the amount of power. At that point is when the batteries began to die out.
Okay, so our total amount should be theoretically about an hour. It should, based upon the battery pack that we use, should run for about an hour and 15 minutes. So essentially, we took I believe it was around 12.6 watt hours that each particular battery could run at. So multiplying that by the 8 that we used, that comes out to about 100. And then with the power that we used is I believe it was 16 volts at 5 amps. That's 80. So taking 106, dividing that by 80, we get about 1.25 hours, which is roughly about like 1 hour and 15 minutes.
Who's this product supposed to be for? Because you said it's for the general public, but is this like targeted for like marathon runners or?
Oh, well, like we said, the general public, but probably the more appealing audience would probably be like sports organizations or teams where their players are outside exposed to this heat and get exhausted. So that'll probably be the primary focus. But our sponsor, his wishes or his goals is to basically make this available to everybody. But yeah.
You said this costs $360 to make?
Correct.
And you said it gives you about an hour and a half or an hour and 15 minutes of cooling?
Yes, correct.
So why can't I just buy a cooling vest for $55 that gives me 3.5 hours of cooling at 100 degrees heat?
Talking about the marketplace to me, current design of cooling glasses.
Yeah, I'm asking why would I buy this over something that I can buy for $55 that is readily available on the market?
Well, the thing about a lot of options available today, for example, one design is you can cool yourself with water, but you would have to have a portable cooler with you at all times. So that's very inconvenient for someone who's walking around. Other designs incorporate the use of, let's say, like freezer packs, for example, and they orient them around the vest. Well, the problem with that is once those things, they use up they're not frozen anymore. You would have to refreeze them in order to use it. At least with this system, you can just put in water at you get a bottle of water, you put it in there, turn on the pump, you start chilling it, and you can send it through. So it's more convenient, I guess.
Ideally, we have like a ways to go in terms of making it, so that it will last longer. But yeah, for now, there's nothing that we know of, at least on the market, that in our studies, where can generate your own cold instead of having to use outside sources, outside frozen water, and lining it up with your vest or your garment in order to cool your body down.
So actually these vests, you grab the vest, you dunk it in water for 3 to 5 minutes, and then these vests are actually used by like high intensity athletes in the Olympics. They're used by people who ride motorcycles across the desert for several hours at a time, and the water that it requires is roughly about a bottle and a half of water for 3 to 5 hours of cooling. And they weigh 2 to 5 pounds, 2 to 8 pounds, but it's distributed across your body. So I'm just struggling to see how something like that would not be cumbersome to a high performance athlete, because they can wear this during performance to prevent them from overheating.
Well, we chose our target time to be 15 minutes because based on what you said, John Pollock, you have about 15 minutes of break time between sessions or what you're doing, either hard exercises or athletic performances. So you can definitely plan to make them put it on, cool them down, play with it 15 minutes, take it off, and go back to what are we doing, what our teams are doing.
To answer your question, athletes aren't going to be the only ones to use this. For an example, a hurricane could hit a country like Haiti, and they probably don't have a refrigeration system where you have another cooling vest that they have to put in aside for to cool other people. So this would be the perfect product for people to actually wear to just walk around in. You don't have to use as much energy. You don't have to use. For another example, there's another product out there that you have to have a lunchable box and put ice in, and when it's exposed to heat, it basically cools you down no more. So essentially, there's a lot of improvements that can be made. This is a real good start for it. So to answer your question on that,
I think that the fact that you need to replace the batteries, especially if you're staying in a country like Haiti where you have lack of resources, is something that's going to be very difficult to do.
Future improvements down the road, like the initial prototype, but you said we want to maximize.
Yeah, I guess encompassing all this conversation with the weight, the time of cooling, and the encumbrance of having this system deployed anywhere, either for EMS services to sports figures and so forth. One of the things that actually would help drive this is the delta T that you have per cost per weight relation. If you have that right off the bat, you know definitely where the improvements are going to go. Weight, we probably know how much it'll weigh depending on how much cooling you need, depending on what materials, depending on the surface area, and so forth. If you have that comparison right off the bat of how much delta T do you need for that square footage of space based on the cooling capability of your system, you can now decide whether you improve on a battery system that it's probably lighter but better, or a cooling fluid which is not water, it's a self-contained system which doesn't need anything. It's a glycol based, let's say, right? And you don't have to, you could forget about pouring water over it. Instead of batteries, you could also include power cells, solar cells into it. You're on the outside. So the relationship here and the cost issue is very important, because that's going to dictate where you're going to start enhancing the efficiencies of your system. If cost per weight, your weight issue is the highest, you tackle that one first. If your power issue to delta T is your biggest concern now, then your Peltier, your R's between your Peltier and your acrylic box or your aluminum tank is the one that you have to tackle first. So I would say that the focus here is your cost relationship between the objective itself. How much delta T do you need per square area of the body given the pertinent conditions, right? If you tackle that, then you start optimizing where is it that you're gonna put the most bang for the buck, right? Right now you have $315, goes to his questions like, why wouldn't I buy a regular off-the-shelf, cooling vest? Versus you can say, well, I can improve 50% on this with a specific material or different system. Instead of Peltier, or not Peltier, but instead of water, I could use glycol and further increase the efficiency of that, right? So having that relationship, cost relationship with the delta changes that you're looking at is the way to push forward on your optimization. So think about that.
The question I want to ask you is, if you were doing it over today and you were designing it for usability, how would you change this design? Okay, anatomically accurate, something that's easy to use, something that I would pick off a shelf because it makes sense, it would work for me. How would you change this design today in order to meet those kinds of requests?
Feeling?
Yeah.
Well, I mean, maybe people kind of base it on looks, so like maybe a more trendier kind of material, like things like Under Armour kind of. The way
I'm not even thinking there.
Okay.
This weighs a lot.
Correct.
It's on your back. It's hanging off the back of you.
Well, you don't.
It's got multiple components within it. Those components geometrically don't have to look like that. You could distribute that load across the back. Heat exchanger. You've got a lot of surface area on your back.
Yeah.
Use it.
6 fans, all even.
Yeah. And now all of a sudden it's not big and bulky.
The front will be thin. But neoprene, you said, is a good insulator, so it's going to insulate your front too. So I will make your front something that breathes, so you don't have heat collect, held up at the front. But
No, you are right about the weight. I just will mention one thing though. When we actually put on the vest, you actually do not. The weight of these materials is actually very. You don't really feel it. It actually conforms pretty well with the body. But
How much does that total weigh?
Well, we didn't get it.
Okay, so we haven't actually weighted with the vest. However, with the tubing and with that entire system, heat sink, fan, water block, with water inside of it, weighed about 7 pounds.
Did you wear it around for one?
Yes, a little bit. Another thing we would also change is when we actually got the exterior neoprene vest, we forgot to take consideration of when we go to insulate it. Our initial idea was to cover the entire surface area of the body. So when we went and tried to line it, obviously like the insulation rubber isn't as flexible as the outside. We actually bought an XL thinking we had a window for that. However, it didn't necessarily happen. So we had to limit the amount of insulation that we did. So also we tried to just make sure that it stays like where you can move your arms and it's still breathable. And we also would like to cover more surface area both on the back and on the front as well, so that there's an even distribution of cooling throughout the entire system.
Yeah, but you're right.
Go ahead,
Your body model showed that the concentration is, from the looks of it, in the middle of our back.
Mm-hmm.
And did you find that to be true when you wore this, since it looks like the concentration of the coolant was in that area?
Yeah.
Did it kind of cool you all over just from being in that area?
The initial effect, like the effects of it, like when actually wearing it, you feel colder on the back, but like it wasn't something that we wore enough times to see like how's our total body, and also we weren't in like Michael said earlier, we weren't in like really hot conditions, so we couldn't tell ourselves like did this significantly drop it to where I'm comfortable now, even though I'm standing in the hot sun, So those were definitely things that we will be looking into later when we get a chance to do those experiments for the sake of our sponsor.
It looks to me like if you slip it up, something like an Army flak jacket. These guys are going to the desert, are fighting, would love to have something like this.
Right.
And the modifications everybody was talking about, making it slicker, would probably be an advantage.
Design process, right? You start with the initial and then
Right.
you work your way out.
Get an Elon Musk battery, and
Correct.
Is 20 Fahrenheit delta T enough for the applications? The difference between your system was about a 20 degree Fahrenheit change. Is that adequate for the applications? 100 degrees C down to 80. Is that where you want to use this, or do you want to use it 100 in the Arizona desert, 120 degrees C down to 80?
The most ideal situation for this vessel probably like in those extreme conditions, but we kind of just designed it for the general temperature of Miami, things like that. But based on the thermal analysis, or heat resistance.
Yeah, because the fact is like also, like, for example, Arizona, it's less humid, right? So we had to, when we were actually designing it, we had to take a certain area and say, what's the average temperature been, you know, on the scale of this amount of time, and that's why we stuck to just Miami for now. Just so, because there's just different climates when you go to, everywhere has a different form of hot, you know, so.
Think about cooling, or
Yeah.
it's a subjective thing, you know, like maybe at a certain temperature I feel cold or comfortable, maybe James might think, no, I need more, or, you know what I'm saying? So we have to work around with it and see how we can get the best fit option to,
But
you know, please.
to answer your question, based upon our theory and what the answers we came out with, it was feasible enough to remove that 44 some odd watts of heat from the human body at that 92 degrees Fahrenheit.
Yeah.
I will make the vest white as well.
Oh, yeah, to reflect. The radiation, effect of radiation, yes. Any other questions?
Well, thank you very much.
We're moving to theme number 7.